Okay, so I'm just going to draw this one. So we've got a roof. From it is hanging an inverted A. Like this. And we've got it hanging from two strings. Like this. And the length is equally split, where that is L and that is L, and this is also L and L, even though it might not look like it. And so it wants to know what force the crossbar applies on the sides, and not just what force the crossbar applies, or sorry, it's not just that. So we have masses for our sides here. So each of the legs has a length of 2L and a weight of 120 newtons, and the center we can put there. So the weight here is 120 newtons. And it just wants to know the force applied by the crossbar. So first of all, we can find the values of our tensions here by using F equals ma. So if we've got 120 newtons there, and we've got 120 newtons there, and so from F equals ma, or the sum of our forces equals ma, we know this equals 0 as it's not moving. Our only forces here are our tension forces, and we would assume, as it's equally distributed, that both tensions are actually the same. So I'm just going to leave it as T plus T, like that. And then plus our weights, which is 120 equals 0. And so we can easily see that our tension here is 120 newtons. So each of the tensions are 120 newtons. So now if we consider this rotational point, that way we don't have to worry about the force of each leg on the other one. So that makes it a bit easier. And so the forces here are a gravitational force, our force due to our crossbar, which I'm going to label as Fc, and our tension. And I'm going to just solve it the way I've got it all drawn out here. And it does give us that this angle is 60 degrees. All right. So now for each of our tensions, or to solve this now, we need to use that some of our torques is I alpha, which is 0 because it's not moving. And now we need to figure out each of our individual torques. So let's start off with our crossbar, and I'm just going to re-sketch it here. So we've got an R of L, and then we're applying our crossbar force. To calculate our torque, which is F cross R, we need our angle, because we can rewrite this as F R sine theta. And to get our angle, we need to put these two tail to tail. So our FC is actually here, and so we need this theta. So we're given that we've bisected this angle here, so this angle in here would actually be 30 degrees. This is 90. So our theta in this case is FR sine 90 plus 30, which is equal to FR cos theta, or FR cosine of 30 degrees. Which, if you're good with trig, you'll recognize that as root 3 over 2. Also, we need a sine on this guy, and so we're going to again use the right hand. We're going to use the right hand rule, and so the way that I do it is put our fingers in the direction of the force on your right hand, and then your palm is in the direction. Those are roughly fingers. Our palm is in the direction of the L, and then your thumb is in the direction of the force. So in this case, it will be out of the board or out of the page, which I'm going to define as my positive. That is not a very nice hand, but it's okay. Okay, so then there's our FC torque, and now our mg torque, or our mass. So our torque, I'm just going to redraw it again actually. So that the mg torque is going to be applied at L. So our R is L, and our mg is 120 newtons. And again, we're going to put it tail to tail. And it's this angle in here that we need. Again, it bisects the angle, so that would be 30. In here would be 60. And so this angle is 60 minus 90. So our torque is F cross R, which is F R sine theta, which is F R sine of 60 plus 90, which is F R cosine of 60, which is a half. So cosine of 60 is a half. We do need a sine on this, so our force is downward from the right hand rule. Then we would point the fingers downward with our palm facing the R, and our thumb would point in the direction of the force, which is in this case into the board or into the page, giving us a negative torque. And actually in this case, we do have quite a few of the values, and for this one as well, we had quite a few of the values, so this should have been FCR, in this case is L, root 3 over 2. And in this case, we have minus 120 newtons times L over 2, which is just minus 60 newtons times L. Okay, and then for our tension force, this guy is being applied at 2L, and it's going upwards, so there's our tension. That's L. Again, we want to put this tail to tail and find that angle, which is just going to be 30 degrees as it bisects the 60 degrees of the A. And so our torque is F cross R, which is just our tension times 2L times sine theta. And again, and now if we apply our right hand rule, we see that this guy is coming out of the page. So this is a positive torque. and we have all of our values. So that's T times 2L times sine of 30. Sine of 30 is a half, and our tension value is found as 120. So 120 newtons times 2L times a half, which is 120 newtons times L. Okay, so then there's all of our tension values, or all of our torque values. So we have that our sum of our torque is 0, and so this is going to be just collecting them all together. Root 3 FCL over 2 minus 60 newtons times L plus 120 newtons times L. Now rearranging and collecting terms, we can see that FC, and we can cancel all our L's here. FC is minus 60 newtons times 2 over root 3, which comes out to be minus 69.3 newtons. So the negative sign just means that I initially chose the FC in the wrong direction, so it doesn't pull the A in, it actually pushes the A out. But the magnitude of the force is 69.3 newtons. Okay, and so then sets the torques all equal to each other, cancel, and we get that the force of the crossbar is 69.3 newtons. So that looks good.